minutes digital.
Oh, yeah.
All right. So in the interest of getting us to lunch on time, we'll just do this without any interactivity. But so the second lecture today, we're going to talk about beam attenuation. And I may not actually get through everything I thought I might get through, but I think it's okay because a lot of it we're going to come back to in various forms when we start talking about particle size distributions and properties of particles and how those relate to inherent optical properties. So the pieces will come in eventually. But the goal is to start off by talking a little bit about the theory of measurement of beam attenuation following the same format you've seen for the absorption and scattering coefficients so far. So that should be pretty familiar. And then we'll talk a little bit more about the reality of measuring beam attenuation coefficients, which like everything else that I guess you're learning in the labs already, there's always caveats, and for beam attenuation, that's no different. Distribution in the ocean, I've moved. So if we have time, we'll get into applications and what we actually see when we look at distributions of beam attenuation, the coefficient in the ocean. And I'll spend a little bit of time on theoretical predictions. So relating to me theory that Colin introduced sort of qualitatively, we'll talk about some of those predictions for beam attenuation as well. These slides are mostly modified from stuff that Emmanuel did, and you'll notice there's a lot of Emmanuel Boss citations in there, but I've tweaked them a little bit, and Colin also provided, I don't know if she knows this or not, but
She doesn't care.
okay. All right, so you've seen a version of this diagram so far already for absorption and scattering, right? So we're thinking about the loss of your incident radiance flux as it passes through some infinitesimally small layer of water with delta X, which is not labeled on there. But in this case, we're only now thinking about the attenuation of that light, what makes it through to the other side as our transmitted radiance flux. So the light might get absorbed within our layer. It might get scattered in all directions. Theoretically, we don't care, right? We're just looking at what makes it out the other side. So, so this is what's going to form the basis of our beam attenuation coefficient. And the thing I was going to write on the slide is this very, very simple, I don't know who thought it up, A plus B equals C, right? Very, very simple equation that underlies optical oceanography. So the beam attenuation coefficient C is just going to be the total of your absorption and total scattering. So pretty straightforward from that perspective. I'm not going to hang a long time on this math because, again, you've already seen it twice from Colin, but I can, if you want, we can go through it. But basically, we're thinking about the loss of light as we go through our layer, right? So we can think about the attenuance, and the beam attenuation coefficient would just be, C would be the fractional attenuance per unit distance as you go through. And so we define it in basically the exact same way we do the absorption coefficient, right? So it's the log of the transmitted to incident light divided by the path length, the opposite of the path length. Okay, is this pretty straightforward, clear at this point? Okay, move on. So that was the theory I just talked about. The reality, which should sort of step right on from what Colin, or step right forth, I guess, from what Colin was saying at the end of the scattering lecture we just went through, is that when we measure beam attenuation, we're looking at the light that did not get absorbed, did not get scattered, and we're trying to detect that with a physical detector. So of course we can't make a detector. It is impossible to see an infinitesimally narrow solid angle of view, right? So you're always going to collect a little bit of that forward scattered light when you measure beam attenuation. So this triangle here, which you'll see a version of that appear in various other diagrams that I make, as well as our narrow but not infinitely narrow detector looking there. So the detected flux measurement usually excludes most of the scattered flux, but we always are going to get some forward scattered light. So just as sort of a starting point to think about this, in this little mini table down here, we've got the detector acceptance angles for two of our common, and I think we'll use both list So the laser in situ scattering and transmissometry meter list, type B, I think you guys will work with this afternoon. It actually is going to give you the near forward volume scattering function, but it also provides a beam attenuation measurement. So its beam attenuation detector has an acceptance angle of 0.0269 degrees, and then the AC meters that you're already familiar with, the C side of those have an acceptance angle of 0.93 degrees, just about 1 degree. So just sort of thinking about what we've already just said, with these two different acceptance angles, all other things being equal, which one would you think would give you the larger beam attenuation coefficient measurement?
The smaller angle?
Right, so the list is going to give you a higher value for the beam attenuation coefficient than the AC meter, just because one of them's collecting more near forward scattered light. What if, so it's gonna, sorry, the AC meter will collect more near forward scattered light. I probably said it backwards, and then give you the lower beam attenuation coefficient, right? Because it's going to collect more of that light. And so it's going to say less, okay, less was scattered, more came through and didn't interact with the fluid, when in fact it did. It just did it in the very near forward direction. So your detector can't tell the difference. Do you think that this effect would be more pronounced? So say we have two samples. One of them is some really tiny little mineral particles, like scooped up mud off the bottom of one of the mud flats out here. And the other one is a culture of like rhizostolemia or something, some ginormous phytoplankton cell. If we took those particles, those different samples, and ran them through this pair of instruments, which one would show the bigger difference between the beam attenuation measurements? One with tiny particles, one with large ones. Which particles are going to scatter the light in more the near forward direction? The big, large cells, right? So which, if we have a sample that's got the light being scattered more in the near forward direction, we should expect to see a bigger difference between what the list and the AC meter are telling us, right? So we should see that divergence be more pronounced as a function of particle size. I don't know if that's helping or not.
Can you just like make the detector a lot further away from the sample, and its effective like viewing angle is smaller? I guess you're limited in the water by weight.
Yeah, I think if you made your, that would sort of go into the parameters that define what the acceptance angle of the detector is. Yeah.
But if you put the detector too far away, and now you end up getting multiple scattering. So all these definitions are based on the assumption that your little volume is short enough or thin enough that you only have one scattering event. When you put it way out and you get multiple scattering, then you get what's called the beam spread function, which we'll talk about at the end of the class.
Okay. Yeah. So if you make the path length really long, then I thought you were talking about like
Yeah,
taking it
like in the
air
baffle
distance
tube,
outside
yeah, exactly. Like put
qubit.
baffles in there. There's no.
Yeah, but then you're just designing a different detector.
Right.
Okay, so your acceptance angle effect matters for your beam attenuation measurement. Here are some data that illustrate this, and there's a lot going on the slide, so I'm going to step down from the top to the bottom. So this is our same table of instruments in there, acceptance angles and water, and I've added a third one here. This is another version of the list that's meant to measure really, really large particles and has a very narrow field of view on its detector. So there's our colors that correspond to this top panel here. And we can see, as predicted, we've got these three different realizations of beam attenuation. And this is over time in a tidally dominated coastal system. And so you're seeing the list flash with its really narrow acceptance angles, giving you the highest reading for beam attenuation, right? Because it's excluding that near forward scattered light that actually is attenuated. And the AC9 is collecting the most of that near forward scattered light, so it's got the lowest reading. So we can take the ratios of those different sensors, and here the ratios, I put little colored dots to correspond to what line in the middle panel we're looking at. But you can see, for instance, that our two lists, which both have their narrowest acceptance angles, have a ratio that's closer to 1, right? So they're doing a better job. But there is no way to correct for this effect. So when you report beam attenuation, you need to report the acceptance angle that goes along with it, because it's an inherent part of what you're measuring. You're collecting some amount of scattered light that needs to be accounted for.
I don't really understand if you have a wider acceptance angle and you're getting more forward light plus C, wouldn't it be a higher value? Like, why is?
So you're collecting more, but then that means that your C is going down because the beam attenuation.
Are these values like after correcting for that? After removing the forward scattering light?
So yes, well, it's not removed, it's in there. I'm going to back up and show the equation again. Yeah. Okay. So our beam attenuation coefficient is looking at what's transmitted, right? So we're not thinking about what's been absorbed or scattered. It's just what's transmitted, what's measured is transmitted, right? And so in this case, if you collect more of that, then your C, right, phi t, phi naught, I'm saying it right, is going to get, right, this ratio will be larger, right? And so your C value is going to get smaller.
But in a wider angle, isn't your total phi going to be more, the forward scattering be included in that?
I think you're thinking of transmission versus beam attenuation. And so you're collecting more light. So therefore you're saying less light was lost to scattering. Your water was clearer. Your attenuation coefficient is lower. We didn't lose as much light. But really, that light was scattered. You just said that it wasn't because you collected it, you detected it. And if you detect it, you say not attenuated. So the bigger the angle, you're collecting diffracted light, but you're saying that it wasn't diffracted. You're saying it was unattenuated. So your beam attenuation coefficient goes down. The loss per meter is less because some of the photons that in fact were lost, your detector collected.
I just Googled just the definition of attenuation, and that means reduce the force vector value up. So, because I had the exact same
Yeah.
question.
Yeah.
So essentially, less is getting lost to the other
Yeah.
phenomena that happen.
If all of the light comes through, then phi t and phi 0 are the same, so you get the log of 1, which is 0. So
Right.
all the light comes through means it's 0 beam attenuation.
There's no
So
loss.
the more light you collect, the closer you're making phi t to phi 0, so the smaller beam C becomes.
Okay.
So the analogy is actually very good to the absorption coefficient measurements we made yesterday in lab with no particles, right? In fact, it's the same thing if you have no scattering. Okay. Okay. So I'm going to move forward from this slide. But basically, we're just saying that this is sort of an inherent part of the physical measurement of beam attenuation, is the acceptance angle. And so it's important information.
Is there a relationship between path length and acceptance angle?
No, they're just parameters of the instrument. Yeah.
The ratio one in the middle, I
Yeah.
mean, is then referred to as the histograms below?
Yes, so these ratios then go into the histogram.
Okay,
Yeah.
and then the list B and list flock have the best agreement.
Mhm.
Okay,
Because they have the smallest detective or acceptance angles, right? So they are similarly excluding most of that near forward scattered light. And there's as we saw in the last lecture, there's a lot of light that gets scattered just in those few degrees from 0. Yeah. Okay. All right. So another thing that we need to think about with beam attenuation and our actual sensors that we're using, many of them anyway, is So our definition of the beam attenuation coefficient includes this incident light term, right? Which we don't always actually measure, right? The LIST instrument that you'll meet this afternoon actually does have a sort of internal constant measurement of its own light intensity, its lamp intensity. But for instance, the ACS, right, won't, or the C-star, do we have a C-star? We don't have a C-star, okay. That's a simpler single wavelength transmissometer. We will have a LIST tau, which I suspect does being related to a LIST. So anyway, some instruments do, some don't. So one practice that often gets used for simpler beam transmissometers and AC meters is to use some other reference material, right? And so then here we are measuring our reference, and then we measure our sample relative to the reference, right? So the detected light that passes through, that's transmitted through the sample relative to the light that's transmitted through the reference material is what we use to compute our sample, our corrected sample beam attenuation coefficient. So what are some reference materials that might be good ones to use if you're trying to measure the beam attenuation coefficient in a ocean application?
Pure water.
Pure water, that's a good one. Yeah, if you want to get the total beam attenuation coefficient of what you're studying, then that's a good one to use. But if you don't have a source of pure water, but you're, say, profiling your instrument,
Filtered seawater.
filtered seawater, or if you're interested in the particulate part of the beam attenuation coefficient, actually C sub P. You could do it relative to air. In fact, some older studies, that was pretty common to use the air reference. It's hard to get a good stable air value on a beam transmissometer.
Or a spectrophotometer.
Yep. same issues, condensation, salt, tiny particles, aerosols.
You just cover the sensor, so there's zero attenuation, so then you can see at least if the sensor had any.
So if you cover the sensor, if you block the beam, will it be zero attenuation? It would be 100%, right, total really high attenuation because you're not letting any light through. But that will give you a sensor dark reading, which we will come to in a couple of slides. So that is an important thing to do. But yeah, but a zero for reference here would actually be something that lets almost all the light through. Right? Did you looked poised?
If you were using like a deployed instrument that you can access, could you use like deep water that's relatively constant?
Yep. So bioargo floats, biogeochemical argo floats. Yeah, that's a common strategy to use, is to reference against water in a very clear, sort of particle-free part of the water column. You have to be careful about, is that actually, right? And how does it change over time and space? But yes.
Could you use like a piece of quartz or something for constant refractive?
Yeah, I mean, your refractive index would be very, very different from water, but yeah, sort of similar to air, right? If you're doing an air reference, it's not going to match your sample very well. But yeah, if you had something with known properties, maybe it would help you track your sensor. I don't know if anyone has actually done that, but just sort of thinking. So this works pretty well as long as you've got a stable initial light source. And for instance, some of our ACSs in the lab do not. And so they're being taken out of the rotation, but that's an important caveat as well. Okay, so this is going to relate a little bit back to some of your presentation, I think, this morning, thinking about absorption measurements in your spectrophotometer. But here's a scenario, and it's a bummer that Emmanuel's not in the room because this is actually his scenario. Well, I wrote it up, but he experienced this, I shall say. If you collect some LIST data in the Dead Sea, which has massive salinity, right? It's like super saturated, 270 grams per kilogram of salt. And the instrument gives you negative values for beam attenuation. So you collect a bottle sample and you filter it and you put it in your spectrophotometer in a 1 centimeter cuvette. And it's even worse. The problem is even worse. And then both of your measurements you've referenced against the same millicu. So you know you're not, dirty millicu or something like that. So what's going on? Yeah.
I just want to clarify.
Yeah.
This would mean theoretically we're adding light.
Maybe not adding light, but if you have a negative beam attenuation, then that implies that phi t is bigger than phi naught.
Yeah.
Yeah.
It's like amplifier. It's like
Yeah.
multiple
Yeah.
scattering going into the sensor.
So we could have multiple scattering, but we've got a filtered bottle sample that's doing the same thing. Did you guys get some negative absorption values in your spectrophotometer? And what caused that to happen? The blank? You had it referenced against air, right? Yeah, so we had some refractive index differences going in and out of your cuvette versus your sample, your cuvette filled with air versus your cuvette filled with sample water. So in this situation, what was actually going on had to do with the fact that whenever you're sending light into a transmissometer or a spectrophotometer cuvette, you're passing through refractive index changes as that light beam goes into the window, right? Or the side of the cuvette. If you're thinking about a cuvette and a spectrophotometer, you're changing refractive index from air inside the instrument to glass, quartz or whatever. And then you're changing refractive index again as you go from the quartz into your sample or reference water. And then you're changing it again and again. And every time that light, which is normal to the window, passes through this refractive index change, there's just a little bit that's actually reflected back, right? Most of it's transmitted, but some of it is reflected. So this obeys Fresnel equation for normally incident light. So there's sort of a solution of this for just the case where the light is coming in at a normal angle. And it depends on the degree of mismatch between those refractive indices. So when you're going from the air to the window and from the window to the air, doesn't matter what's in your fluid volume, right? What your sample water is. But when you're going from the glass to the water, and then from the water back to the glass, both times you lose a little bit of light because of that refractive index change. And in this case, this difference between the reference water, and here DIW stands for deionized water, so this is just reference water, right? That glass to DI water T squared term, right? Because you do it twice, you go in and then you go out again, is different. It's different enough from the sample transmission across that water glass interface that it makes a big enough difference. So the transmittance here, we can take as the ratio, right, of the sample to the reference water, includes these terms for sending the light through the glass water interface. And if you work through the math, it turns out that the beam attenuation coefficient that's measured, so log of the transmittance over the path length. So if you take the difference between the sample and the reference, there's also this additional term that you would have to subtract to correct for the fact that the refractive indices of, in this case, 270 grams per kilogram of salt water versus DI water. It's really big, right? So there is this additional thing that has to get subtracted. And if you assume it's zero, which we usually do because it's close to zero in our typical regular seawater, the refractive index is not that different enough to cause this problem, then you end up getting negative beam attenuation. So it's probably not something that you would run into in a lot of situations, but it's important to remember that if you have a refractive index in your reference that's really different than your sample water, you might need to make that correction. Yeah.
You add the last negative from 2 over L log, that's the bit you add in.
Yeah, so this is sort of, you subtract it, but it's an additional correction that might be necessary. And it will be something, if you look in this term, there's a divide by the path length in there, right? So if your path length is short, it will be more pronounced, the effect. So you might see it more easily in a spectrophotometer or a list with a 5 centimeter path length than you would, for instance, in an ACS. So we don't really worry about it with ACS and normal seawater, but
Do you know,
yeah.
happen to know what the index of refraction of the dead sea water was at the wavelength they were playing at?
oh my gosh, I didn't memorize the number.
'Cause
I just read the paper
I
again
wouldn't
last week.
trust- You know, I have little formulas that
Yeah.
give you index of refraction as a function of temperature and salinity, but this is so far beyond their
Right.
range of validity, I wouldn't trust them.
Yeah, I think they ended up extrapolating. So the salinity coefficients for the absorption by water also stop at like 100 grams per kilogram maybe. And I think they extrapolated that and it seemed to work well enough.
Okay.
But yeah,
I'll plug in some numbers tonight just to see
what it would be. Yeah. All right, so reference materials, index of refraction might be an issue in some key situations. Another thing to think about is that some sensors don't read 0 when there is no light hitting them. So there could be electrical noise, there could be drift that is uncharacterized. And so this is what you were getting at before, I think, that you want to also measure the dark signal and remove that from both your sample and your reference measurements. And for transmissometers, blocking the beam will give you an estimate of that. There's also a factory dark. Factory dark sometimes is useful, but sometimes it's not. So it's good to check. Yeah.
Never mind.
Okay. I'm not going to say for transmissometers, but for scattering sensors, dark sensors sometimes depends on like what your power source is to your instrument. So you want to be careful there as well, that you're getting your dark reading from where your sensor is being powered by the same thing that it's going to be powered by when you deploy it or use it for your sample collection.
And sometimes it depends on if it's in fluid or not.
Right.
Sometimes they don't have electric stability,
Oh.
and so the dark would be different if it's in air or in freshwater or in saltwater.
Really? Fresh or
And usually all
salt?
of the eco sensors were that way, and they've corrected it, but if you're working on a new sensor, just check.
Yeah.
Make sure, sometimes they're just not,
It's an easy thing to check.
grounded well.
Yep. All right. So the measurement of beam attenuation, right, in theory should be pretty simple, right? Shoot a light through, see how much comes out the other side. We don't have to correct for absorption. We don't have to correct for scattering. A lot simpler than absorption and scattering measurements. But there's a few things to keep in mind. The acceptance angle matters, needs to be reported. You can't correct for that, right? If you're collecting your forward scattered light, you've collected it. It's not dependent on polarization state or absorption or scattering along the path, like I said. The other thing that's really cool about beam attenuation is that it's been around for a long time. There's been commercial instruments starting, I think, from the CTEC transmissometer back in the 80s. It's been measured for a long time. So it's probably our longest time series that we have of measurements of an IOP in the ocean. With all these caveats that you need to know all these things and know that they were taken care of correctly. All right, so this is sort of the measurement part of things. Where am I for time? 11:42. Okay, half an hour. All right. I think this is important. So this is a scenario that happened to me. It probably has happened to some of you. It probably will happen to many of you in the future. If you go on like a UNOL ship and the CTD rosette has a C-star transmissometer taped onto it or something, and it's like unknown provenance. You don't know when it was last calibrated, but you really want to use the data because yours didn't make it through FedEx or something. What do you need to do? What info do you need to get from the ship's technician or find out on your own. These things.
Outputs and analog or digital.
That, okay, yeah.
And I had to convert it a little.
Okay, so yeah, sometimes they'll give you digital counts, sometimes they'll give you an analog voltage that goes through the CTD. Yep,
Acceptance angle.
acceptance angle.
But it is a dark measurement.
Yep, if there's no dark measurement or they don't know what it is, can you do something about it? You can just block the beam and get a dark measurement.
You know what your bright voltage is for
Okay,
max or attenuation.
so you'd like to know what your reference is? What if you can't put a flow tube on it and get a clean water reading because it lives in a greasy CTD garage and is covered in Niskin bottles or something? Hopefully you can, but if you can't do a millicu calibration on the C-star there on the rosette,
So I don't know, 2,000 meters.
yeah, so you can look and see, okay, where's my, and you have to report that I've referenced this to deep water, right? And think a little bit about your context, but yeah, you could take that approach. Yeah. Okay. Other things I'm not thinking of.
If they have it, when it was last serviced and what its specs were when it came back.
Yeah. They might not know, but
They
they might
also
know.
What the wavelength is that it's.
Yeah. What wavelength is it? Yeah. Okay. I would have been scribbling all these things down for posterity, but do you have any other?
He's scribbling them down.
You're scribbling them down. Okay, cool. Great. Okay, so we're gonna now sort of think about beam attenuation from the theoretical side. So knowing that there are all these caveats and things we need to think about when we're measuring it. We can use, so Colin spoke very briefly about me theory, which is basically a solution of Maxwell's equations applied to homogeneous spheres, which ocean particles in the ocean are not homogeneous spheres, and you'll hear this many times in the course as we go along, but it's a useful approximation, particularly for phytoplankton-like particles, for things, you know, we can get some good approximations and especially good predictions and insight into what's going on by using it. So what I'm going to show you in the next few slides are output from a me model that Emmanuel ran and that you guys will be learning how to run, I think on Monday afternoon's lab will actually be, you'll get some codes and learn how to do these predictions yourselves. So what we're looking at here is a plot of the attenuation cross-section of a single particle. And that particle is allowed to vary, has size ranging from 0.1 to 200 or 100 microns on our log scale on the horizontal axis. And then what we're looking at when we think of an attenuation cross-section of a particle, it's not a geometric cross-section, right? Where you're just thinking about what's the area of this sphere, but it's rather, you can think of it as the optical surface area, right, that it's presenting. Another way to think about it would be if you took this single particle with its attenuation cross-section, and this should be a capital C actually, not a lowercase c, so that's a typo. And you took that single particle and you put it in a volume of water. So one particle, stuck it in a cubic meter of water, then there would be this optical cross-section, units of area in volume of water, cubic meters. What would within that volume, you would end up with an attenuation coefficient with units of inverse meters as expected, right? So you can think about this cross-section being the contribution within some unit volume of a single particle or population of particles if you model a whole bunch of them. So that might be kind of a way to get some physical intuition about what this is. But basically what this line is showing us, this blue line is maybe, kind of makes sense. As the particle gets bigger and bigger and bigger, it's going to scatter and absorb more light, right? You're going to see an increase in the optical cross-section of that particle.
Is
Yeah.
this for like the volume that will attenuate all of the light that you shine at a particle with that volume kind of, or no?
No, I don't think that's probably the way to, like the volume that will, so when you ask about the volume, you're talking about like if I put it in a cubic meter of water volume, or this is the area that will.
The area when you, I don't know.
Wait, so are the axes, like the bottom is the diameter
Mhm.
of this particle,
Mhm.
and the top is the area that will stop light.
It's the area that interacts is the way I would think about it. So not necessarily that completely attenuates the light.
And
Because of complete attenuation of the light, you want to think about the volume that it's in as well, right? That's kind of our, when we define all these properties, we're thinking about the redirection or absorption of light as it crosses some dx, right? So
how can it be bigger than the diameter?
yeah, can you hold that thought?
Okay.
Okay. All right. So next parameter that we're going to think about is this Q, which is the symbol we use to talk about efficiency factors. So this would be the, sometimes it's called the extinction, and I guess that's more old-fashioned, right? Or attenuation efficiency, Q sub C. So this is the ratio of that optical cross-section that I just computed, showed on the last slide, to the geometric cross-section. So that is literally the geometric projected area of the particle. Again, is a function of particle diameter. And now it's non-dimensional. Yay, non-dimensional. So we've got, we see that it's pretty low for particles that are really small, right? And I should mention these are all modeled at 650 nanometers, right? Which that'll become relevant in a minute. So it's low, right? When particles are really, really small, they're not scattering as much, right? And then its efficiency increases, and then it has these sort of vibrations, these nodes, it goes in and out of phase. And then as we get to really large sizes, it settles out at a value of 2. And this should still make you scratch your head if you're thinking, like as you were just now, why is it 2? Shouldn't the extinction efficiency or the attenuation efficiency of a particle that's really big, shouldn't it be 1? Shouldn't it block out all the light, right? If it's really big. It actually turns out, this is where I really want to draw on the board, but I can't. If you have a particle that's large relative to the wavelength of light, you can imagine that it's totally absorbing all the light that goes into it, and it's diffracting the light that comes around it into a near forward direction, but we're in theory land right now, so we assume that none of that near forward scattered light contributes to the beam attenuation, right? We're excluding it all because we have a perfect sensor. So in that case, you should have an extinction efficiency of 2, because you're diffracting light around the particle and you're absorbing stuff that's incident on it. Maybe you're reflecting a little bit off the surface that is the first surface that the light gets to.
So is this all still me, or is like the Rayleigh the lower end of this?
So this is all in me model, and me actually will tell you something about a large size range. It just, Rayleigh and all these other approximations are kind of simplifications of me theory for specific conditions of refractive index and size.
So it ends up that the absorption and scattering, diffraction, reflection are equal, or are they always just summed up to 2?
They would, for a large particle, they would sum up to 2,
Okay.
right? So they sort of reach a limit. Can be more than 2, right? At the right size, can be less than 2. And this would depend. So this is a particle that's phytoplankton-like. So it's got fairly low relative refractive index relative to water and a little bit of absorption, right? But this, yeah, could vary depending on the properties of that particle.
Okay.
And you will have an opportunity to really dig into that in a lot more detail once you start doing the modeling yourself. And I think Kurt will probably talk about it in a much more detailed way. Emmanuel certainly will on Monday. So there'll be more. We're just kind of getting a qualitative overview here.
So for this one, we have most of the light going through the particle, even when it's large, not getting absorbed, period.
It is getting absorbed if it's large. So when we get, are you talking about here?
Yeah.
Yeah, so it goes in, it can be absorbed or it can be scattered. But if the particle is very large relative to the wavelength of light, in theory, the efficiency should converge to 2.
Okay, so the peak where it goes to like 3.5 is where you have light passing through and light getting diffracted.
Yes,
Yes.
and there's more diffraction. There are certain sizes that resonate.
Mm-hmm.
And so you're getting, in the end, you're getting twice the area. So diffraction accounts for one area around the particle. But at certain sizes, you can get light even farther away from the particle will be diffracted, and that's how you can get a greater value than 2. Because obviously, if it's a huge particle, remember we talked about how you could absorb all the light yesterday? A very huge particle could absorb all the light, but only in its cross-section, its geometric cross-section. So it maxes out to 1. Because of diffraction, you get a number greater than 1.
And I know we're out of time, but Emmanuel was saying during the lab that there's like this section where you get the best bang for your buck on size, and so that's that peak, and that'll shift with wavelength a little bit.
Yes. So this will shift with wavelength, and I'm gonna. We'll see whether we get to it on this lecture, or whether it comes in another one. But you can actually normalize size to wavelength, right? And then you get this nice collapsing down of all these peaks together, so you can really see that. Okay, but yes, more is coming on that one. Did I do it here? Sort of. So this is just one more way of thinking about this, which is to take that, we're now thinking back to that original optical cross-section, and you divide it by the volume of the particle, right? Then you get this estimate of sort of where a beam attenuation is going to be the most sensitive as a function of particle size. So we can see that there is sort of this around 4 microns, right, for this modeled sphere at 650 nanometers. We get this peak resonance, right, with that wavelength of light and that refractive index of the particle. We end up, there's this heightened sensitivity to that size range. And that location of this peak will vary as a function of wavelength and refractive index. Okay, so we talked a little bit about the size dependence of these theoretical models of beam attenuation. So we can also look at the effect of composition, and in me theory, we're using the relative complex refractive index of the particle as kind of the parameterization of composition, right? So a watery particle will have a lower refractive index. And here, the little ends on this plot are talking about relative refractive index. So it's what Colin defined as M in the last lecture. So it's particle refractive index relative to the water. And then as you get to a more mineral-like particle, you're going to end up having a higher relative refractive index. And then the complex or imaginary part of the refractive index refers to its absorption properties. So in this upper panel here, we're looking again at the beam attenuation modeled with me theory divided by the volume of particles in suspension, right, in your model, not in suspension, but in the modeled scenario. And you can see that there's this shift in the sensitivity of beam attenuation as a function of refractive index, right? And it gets, we have a much heightened sensitivity for particles with a higher refractive index that are more mineral-like, and then it increases in size, or size parameter, in this case where we've normalized particle diameter to wavelength, and it decreases in sensitivity as you go towards softer, more phytoplankton-like particles. If we hold the real index of refraction constant, so we're just picking out n of 1.05 on the lower panel here, and then we vary the imaginary part of the refractive index, which is, we're using n apostrophe for that, right? So that's, as this number increases, we're increasing the absorption of the particle. We see that there's not a whole lot of size dependence there, except for we see that there's more attenuation by the very smallest particles as they absorb more, which is kind of consistent if you think about we're getting down into the size range where molecules might be absorbing light. Yeah.
Oh. So is the intuition for the top one that like as you refract more light, more is making it through?
As you refract more.
As more light is refracted, but the lower refractive or? So
the refractive index here, you think of as sort of the change. So if you allow light to go into the particle, right, it's going to slow down a lot more for this high refractive index particle.
So it's attenuating more.
It's reaching a resonance, right, at a different size than it is. Yeah. So I don't know if I would say it's attenuating more.
Oh, okay.
Yeah. I mean,
but doesn't it show that the increase in refractive index there is more too?
Right. So it's attenuating more per particle volume. Yeah. Yeah. Okay. All right. So I've just talked to you a little bit about what the me theory is predicting for solid spheres with these different refractive indices. But it turns out if you go and you measure mass normalized attenuation in the field, or if you do some different modeling, which I'll talk about in a second, we actually only see maybe a factor of 2 variation in mass normalized beam attenuation, right? So this is volume normalized for homogeneous spheres in a me model. If we normalize by mass, we actually we see something a little bit different. And it's, if you guys remember in the first lab, there were the carbohydrate beads that you could see really well. They scattered light fairly well, right, when you put them into the water. And then what happened to them over time?
Took on more water.
They absorbed water. And what did they look like after that in the water? They kind of disappeared, right? So you couldn't, there wasn't as much light scattering off them into your eyes anyway, right? So we saw this, the same matter, right, which is organic matter. These were beads, I think, made out of carbohydrate, something like that, right? It was just being spread out as that particle increased and got, increased its fluid fraction, right? And became more, more watery, basically. So, what we see in the environment is something similar. Particles that when you look at the dry weight of the particles, right? If you filter some particles and you dry them down, you've only got that organic matter that was in there. You lose all that water, right? So the mass normalized attenuation, and in the plot I'm showing here is from a modeling, well, it was an observational study, but here they did me modeling as well of the mass normalized scattering coefficient for non-absorbing particles, right? So if it's not absorbing, then the mass normalized scattering coefficient is the same as the mass normalized attenuation coefficient. They see that if you account for the water content of these organic particles, you actually end up getting mass normalized coefficients that are within a factor of 2 of what you might expect for mineral ones. In this particular graph, the horizontal line is showing the modeled mass normalized scattering for particles that have a really high water content at this end, and then this is going to a lower water content. So you're basically drying out an organic particle, right? But the mass stays the same because you're just removing water when you do a mass normalized measurement. And then all these little dots are showing what you might expect for mineral particles, various clays. I think this one that's all by itself over here is actually opal, which has different behavior than a lot of clays and calcite. So the point is basically that even though me theory is predicting this large variation in volume normalized attenuation for particles of really different refractive indices, in fact, in the real ocean, the particles are often phytoplankton in particular, you can think of as water-filled bags. They don't actually have that much mass in them that's doing that. So the mass normalized values collapse a little bit compared to what the theory predicts. There's a cool paper, if you want to explore this more, by us in 1996 that looks at the refractive indices specifically of all the different organic components that one might find in a cell and sums them all up and makes a model and is able to reproduce the optical properties of phytoplankton. It's kind of old, but a good one. Okay.
Sorry, so
Yeah.
the carbohydrate balls, that's what we saw in the previous graph, essentially, right? Because the index of refraction is getting closer to the water, so it's going to 1.
Yeah, you could think about that. Yeah, I mean, yeah. If you were to take that carbohydrate ball and then dry it out again, the mass would never change, right? So yeah, so here you're looking at volume normalized attenuation. And here we're talking about mass normalized attenuation. And that's what you actually end up measuring a lot of times. I mean, I guess there are some measurements that will give you a particle volume and then you can do a volume normalization. Okay. Where am I for time? 12:04. Okay. So I'm going to speed through a little bit of this and then we're going to save the application stuff for additional lectures where we'll slip it all in. So there's a huge long history, as I sort of hinted at before, because transmissometers have been commercial for a long time. We have a long time series and a lot of people measuring correlations of beam attenuation to things like actually particle volume in this case, total particle volume, particulate organic carbon has a very good correlation with the beam attenuation coefficient. Not as good for particulate dry weight, but pretty good. This figure from a paper by Paul Hill a few years ago compiles the beam attenuation coefficient CP for particles normalized to the suspended particulate matter concentration. So it's basically filter your water, weigh the filter before and after. And you take the ratio of those. We find that for most open ocean environments, which lie between the dashed lines here, the values, again, sort of range through that factor of 2 that the Babin paper was reporting and predicting from modeling. But as you get up to really high, so these are plotted versus the maximum suspended matter concentration reported in each of the studies that also reported this relative, this mass normalized beam attenuation coefficient. So as you go up to really high maximum suspended particulate matter loadings, and these are 10 to 100 to over 100 grams per cubic meter. So we're talking like turbid coastal environments for these. These are not something you find out in the open ocean typically. So as you get into these really sediment particle laden environments, you see lower beam attenuation to suspended mass values. And that is thought to actually be because the particles are larger, right? If you have a muddy environment or a turbulent environment that's resuspending larger particles, then you can end up with a lower beam C to SPM because you've got larger particles and those larger particles attenuate less as a function of mass. Yes?
Is SPM the same? No, what is it different than POC?
Yes,
It's
it
the
is different.
It's different.
They're different, yeah. So the initial part, filtering things onto a filter might be similar, but then one of them, typically SPM, you'll pre-weigh the filter, and then you'll take the filter after you've filtered, and maybe you will rinse off salts and dry it, and then get the mass on a balance very accurately. Whereas POC, you'll take that filter and you'll freeze it usually, sometimes you'll dry it, and then you'll do elemental analysis. You'll burn it up and see how much CO2 comes off. So different numbers. Yeah. Okay, I think now is probably a good place to stop, maybe, because if we go this far, we're going to be here for another 10 minutes. And we've told them, should we keep going? Is it 12:10?
Yeah,
We should stop. Okay, cool. But we will see some of this stuff as we come back in and start talking about applications and proxies and things like that.
And I would note that when Meg was talking about the sizes to which the beam attenuation measurement is sensitive to, remember she's like, it could be small mineral particles or large spectrophotometer. If you look further into the file from this morning, there's a similar graph, and it's also showing that same relationship for backscattering. So by looking at the two, you can see which particle sizes are best detected by which optical measurement between backscattering and beam attenuation. So if you just kind of wade through to the end, you'll see it's comparable. So I just want to tell you